Have you ever dreamed of stepping through a magical doorway and instantly traveling across galaxies or even through time itself? Movies like Interstellar and Avengers have popularized this fascinating idea, showing characters effortlessly crossing vast cosmic distances through wormholes, mysterious tunnels in space-time. But is this purely Hollywood fantasy, or could wormholes actually exist in reality? You might be surprised to learn that wormholes aren't just products of filmmakers' imaginations. In fact, they're a natural prediction stemming directly from Einstein's theory of general relativity, scientifically known as the Einstein-Rosen bridge. Yet the crucial questions remain. If wormholes truly exist, are they stable enough for travel? Could humanity ever create or utilize one to journey across space and time? In this video, we'll explore the intriguing concept of wormholes, from their fundamental nature to the toughest scientific puzzles, in clear, understandable language, enriched by vivid visuals to help you grasp and remember these fascinating ideas. Basic concepts of wormholes and the Einstein-Rosen bridge. The story of wormholes begins in 1935, when two legendary physicists, Albert Einstein and Nathan Rosen, proposed a groundbreaking concept now famously known as the Einstein-Rosen bridge. Their revolutionary idea aimed to explain the theoretical possibility of connecting two distant points in space-time through a kind of shortcut or tunnel. Essentially, this was their attempt to provide a mathematical solution within Einstein's own gravitational field equations. However, Einstein and Rosen's original concept encountered a significant issue. While mathematically elegant, their proposed bridge was fundamentally unstable. It would theoretically collapse almost instantaneously after forming. This inherent instability posed a significant challenge, prompting further scientific exploration and debate. Noted physicist Thorne captured the essence of this problem vividly, stating, "A wormhole is like a doorway through space and time. But the crucial question remains, can we keep this doorway open long enough to pass through it?" His words underline the practical difficulty that scientists still grapple with today. To visualize this complex idea more intuitively, imagine wormholes as tiny tunnels passing straight through an apple instead of traveling around its surface. This simple visual metaphor helps demystify the abstract nature of wormholes, making it easier for us to grasp and retain the concept. From these foundational ideas, we now have a clearer picture of what wormholes are and the intriguing problems they present. With this fundamental understanding, we're prepared to delve deeper into the complexities surrounding wormhole stability and the fascinating, albeit hypothetical, concept of exotic matter, essentially the mysterious material that might just hold these cosmic tunnels open. Stability issues. Wormholes collapse without exotic matter. Let's tackle a major hurdle in our wormhole story head-on: stability. While mathematically fascinating and theoretically possible, wormholes have a significant limitation. They typically collapse almost immediately upon formation. Think of wormholes like soap bubbles, beautiful and intriguing, but incredibly fragile, bursting just moments after appearing. Here's the catch. According to physics, wormholes could theoretically exist. On paper, the equations check out perfectly, demonstrating that a wormhole can connect distant points in space-time. But there's a massive gap between mathematical theory and physical reality. In practice, without something extraordinary to prop them open, wormholes don't last long enough to be useful. They vanish almost instantly, leaving scientists scratching their heads. This problem arises because the gravitational forces inside a wormhole naturally want to collapse it, squeezing the tunnel shut. So far, the only known way to counteract this collapse is through something scientists call exotic matter, which essentially possesses negative energy. This exotic matter, though mathematically valid, is not something we've observed or created in our labs. At least, not yet. So why does this matter to you and me? Because understanding this limitation helps us appreciate the challenges and incredible opportunities that lie ahead. Right now, we're at the exciting intersection of theory and future possibility. Research continues tirelessly, driven by curiosity and the dream of making science fiction a reality. As we look ahead, the work of physicists like Kip Thorne and Michael Morris, who proposed practical ideas for making wormholes traversable, opens new doors and keeps our hopes alive. Let's explore next how their groundbreaking theories might someday turn wormhole travel from fantasy into reality. Traversable wormhole, the concept of a passable wormhole by Morris and Thorne. In 1988, at the California Institute of Technology, Caltech, two visionary physicists, Michael Morris and Kip Thorne, introduced a groundbreaking and surprising concept to the scientific community: the traversable wormhole. Their bold claim suggested that theoretically, wormholes could be stable and safe enough for humans to travel through. Morris and Thorne weren't just chasing abstract ideas. They were genuinely motivated by a deep curiosity about the practical realities of space-time travel, inspiring us to ponder, could we actually harness wormholes to journey between stars or even across time itself? To understand their proposal clearly, let's imagine wormholes as tunnels connecting two distant points. Previously, we saw these tunnels collapse instantly, but Morris and Thorne proposed a solution involving what's known as exotic matter, a strange substance possessing negative energy. Now don't worry, negative energy isn't as intimidating as it sounds. Simply put, it's energy that behaves opposite to gravity, effectively holding the wormhole open. Think of it like placing a sturdy frame inside our fragile tunnel to prevent it from collapsing. Exotic matter, though still theoretical, acts as this supportive structure. This brilliant but challenging idea raised exciting questions. Can humanity produce exotic matter? Could we ever gather enough to stabilize a wormhole for meaningful travel? These intriguing possibilities push the boundaries of our imagination and the limits of modern science. Kip Thorne beautifully captures this sentiment, saying if we could control wormholes, we wouldn't just transform space travel, we might fundamentally redefine our understanding of time and reality itself. This profound insight paves the way for our next fascinating exploration. If wormholes can indeed facilitate travel through time, what intriguing and potentially troubling paradoxes could emerge? Wormholes for time travel and the causal paradoxes they create. If wormholes truly exist and we could use them to travel through time, are we potentially creating opportunities to alter the past and thus generating profound paradoxes? This intriguing possibility invites us to consider the deeper implications of wormhole-driven time travel. As renowned physicist Stephen Hawking once warned, time travel through wormholes could result in paradoxes that we currently have no way to resolve. This caution highlights the complexity and potential risks associated with time travel. One famous example, often cited by scientists, is the grandfather paradox. Imagine traveling back in time and accidentally preventing your grandparents from meeting. This action would prevent your own existence, raising an impossible contradiction. How could you have traveled back in time in the first place? Scientists are actively debating this perplexing issue. Some argue that paradoxes are possible and represent genuine threats to our understanding of reality. Others believe that the laws of physics inherently protect against such paradoxes, meaning that any attempt to create a paradox would inevitably fail. To help simplify this complex issue, scientists refer to the concept of closed time-like curves, or loops in time, where events continuously circle back upon themselves. Imagine walking along a path that eventually loops back to your starting point. Except, in this case, the path is through time rather than space. Such loops could theoretically allow paradoxical events to occur, although whether this is possible remains deeply uncertain. Regardless of the theoretical paradoxes, the study of wormholes and their implications for time travel is compelling precisely because it challenges our fundamental understanding of reality. Resolving these paradoxes remains one of the most captivating and important scientific pursuits, setting the stage for exploring yet another fascinating topic: the intriguing relationship between wormholes and black holes. Interactions between wormholes and black holes. How are they related? Have you ever wondered if wormholes and black holes are somehow connected? It's a fascinating question that scientists have been exploring for decades. To understand this better, let's imagine wormholes as secret tunnels hidden beneath a vast landscape, and black holes as gigantic, deep pits along your path. Could these tunnels perhaps lead into or out of these mysterious black holes? In fact, the scientific community has long considered this intriguing possibility. Early theories suggested that wormholes might naturally form as counterparts to black holes, connecting different regions of space-time. Picture it this way: a black hole might be like a cosmic entrance, pulling everything into its depths, while a wormhole could potentially offer a hidden exit or even a passage to entirely different regions of the universe. Yet the relationship between wormholes and black holes is far from simple. Scientists have encountered numerous challenges and heated debates when attempting to clarify this complex interaction. For instance, while black holes are confirmed astrophysical phenomena with enormous gravitational pulls from which not even light can escape, wormholes remain theoretical constructs whose existence and properties are still uncertain. To make these ideas easier to grasp, think of a black hole as a massive whirlpool in an ocean, pulling everything nearby into its center. A wormhole, in contrast, might be seen as an underwater passage that bypasses this turbulent region, potentially allowing travelers to emerge safely in calmer waters elsewhere. Ultimately, although wormholes and black holes differ fundamentally, understanding their connection could be essential. This link might just be the key to unraveling deeper cosmic mysteries, paving the way for future breakthroughs in space and time travel, and profoundly expanding our understanding of the universe itself. Well, we've certainly had an incredible journey exploring the world of wormholes, haven't we? Imagine a future where stepping through a doorway instantly transports you to distant planets, or even lets you travel back in time to meet your younger self. Exciting, isn't it? As physicist Thorne once said, wormholes could be the key to breaking through the barriers of space and time. But this key still holds many unsolved mysteries. Throughout our adventure, we've tackled these complex ideas step by step, using simple analogies and vivid images. We've encountered exotic matter again, and while it sounds mysterious now, perhaps someday it could become something familiar and practical. Sure, conquering wormholes presents major challenges, but human curiosity and our relentless drive to explore will undoubtedly lead us to discoveries we can't even yet imagine. unlocking incredible new horizons.